The Earth keeps secrets. Buried beneath layers of sediment, pressed between folds of stone, encrypted in the very chemistry of ancient rocks, there may lie evidence of something we've never seriously considered: that we are not the first. Not the first to build cities that pierce the sky, not the first to harness fire and forge metal, not the first to look up at the stars and wonder if we're alone. What if, millions of years before humanity took its first stumbling steps across the African savanna, another civilization rose, flourished, and vanished, leaving behind traces so faint that we might never recognize them for what they are? This is not science fiction. This is the Silurian hypothesis. The name itself comes from a television show, from Doctor Who and its race of intelligent reptilians who supposedly ruled Earth before mammals inherited the planet. But don't let the fictional origin fool you. In 2018, NASA climate scientist Gavin Schmidt and astrophysicist Adam Frank proposed this thought experiment with deadly serious intent. Not because they believed ancient reptilian overlords once walked among the dinosaurs, but because they wanted to probe a more profound question. How would we even know? How would we detect the fingerprints of a long-dead industrial civilization on a planet that routinely swallows evidence whole, grinding bones to dust and mountains to sand? The question haunts. It whispers. It unsettles everything we think we know about our place in the grand sweep of planetary history. Human memory is short, desperately, pathetically short. We struggle to comprehend decades, let alone centuries. Millennia stretch beyond the comfortable boundaries of our imagination. And yet, the Earth measures time in millions and billions of years, eons, epochs, periods that dwarf human history the way an ocean dwarfs a single drop of water. Consider this. Modern humans, Homo sapiens, have existed for roughly 300,000 years. Our recorded history covers perhaps 5,000 years. Industrial civilization? Barely 200 years old. We are infants, newborns, less than a heartbeat in geological time. The dinosaurs ruled for 165 million years. The Earth itself has existed for 4.5 billion years. Life has thrived for at least 3.5 billion years. Within that vast expanse, human civilization occupies a sliver so thin it might as well be invisible.
Now imagine another civilization, not human, that rose and fell 100 million years ago. What would remain? The answer might shock you. Possibly nothing we could easily recognize. Earth is a recycling machine, a planet-sized furnace of creation and destruction. Mountains rise and erode. Continents drift and collide. The ocean floor gets subducted into the mantle every few 100 million years, dragging evidence into the planet's interior where it melts and reforms. Rivers carve canyons. Glaciers grind landscapes to powder. Wind scours. Water dissolves. Life decomposes. Everything gets eaten by time. Consider New York City, that monument to human ambition and engineering prowess. Those steel towers, concrete canyons, glass facades gleaming in the sun. How long would they last without us? Estimates suggest most buildings would collapse within a few centuries. Within 1,000 years, nearly all trace of the city would vanish beneath vegetation. Within 10,000 years, only the most durable structures might leave fragments. Give it 1,000,000 years, and even those fragments would erode to dust, leaving perhaps only oddities in the geological record, unusual concentrations of metals, strange chemical signatures, anomalous layers in the sediment. Now multiply that million by 100. At 100 million years, what evidence remains? What detective could reconstruct the existence of a civilization from such faint clues? This is the challenge the Silurian hypothesis poses. Not whether such a civilization existed, but whether we would have the capability to detect it if it had. If we want to play detective in deep time, we need to understand what kinds of traces might persist across millions of years. Physical artifacts? Forget it. Even plastics, those seemingly eternal pollutants, break down over geological timescales. Metal corrodes, concrete crumbles, glass returns to sand. Buildings become hills, become dust, becomes stone. But chemistry remembers.
The most persistent evidence of an ancient industrial civilization would likely be chemical and isotopic signatures preserved in sedimentary rocks. Subtle anomalies that careful analysis might reveal. Burning fossil fuels releases carbon dioxide with a distinctive isotopic signature. This carbon, locked away for millions of years, has a different ratio of carbon-12 to carbon-13 than carbon cycling through the active biosphere. A sudden spike in fossil fuel burning would leave a layer in the sedimentary record where carbon isotopes shift dramatically. We see exactly this kind of signature from human industrial activity in recent sediments. But could we detect it from 100 million years ago? Perhaps. If the civilization was large enough, lasted long enough, and the sediments survived, yes, plastics degrade, but not completely. They fragment into smaller and smaller pieces, eventually leaving synthetic polymer residues that might persist in certain sedimentary environments. Future geologists could potentially find a thin layer enriched in these artificial compounds, a plastic horizon marking an industrial age. Mining and refining metals creates unusual distributions. A civilization extracting and processing copper, iron, rare earth elements, or other resources would leave behind waste heaps, mine tailings, and sediments with anomalous metal concentrations. Over millions of years, these might appear as thin layers with unexpected geochemical signatures. Industrial agriculture depends on synthetic fertilizers. The Haber-Bosch process for fixing nitrogen has fundamentally altered the global nitrogen cycle. A similar process used by an ancient civilization would leave traces. Sudden changes in nitrogen and phosphorus ratios in sedimentary rocks, anomalous distributions of nitrates, shifts in the nitrogen isotope record. If an ancient civilization burned through fossil fuels or otherwise altered the climate, we might see evidence in the geologic record. Rapid warming events, changes in ocean chemistry, shifts in the types of organisms that thrived. The challenge is distinguishing artificial warming from natural climate variations, of which Earth has experienced many.
Here's a darker possibility. If an ancient civilization pushed the planet's ecosystems to collapse, we might see a spike in extinction rates. But Earth's history is punctuated with mass extinctions, most caused by natural events, asteroid impacts, massive volcanic eruptions, ocean anoxia. How would we distinguish a civilization-caused extinction from a natural catastrophe? The truth is, we probably couldn't, not with certainty. And that's precisely the point. We are living through the creation of geological evidence right now. The Anthropocene, proposed as the current geological epoch defined by human impact on the planet, offers a laboratory for understanding what traces we're leaving behind. Think about it. We are the experiment. Future geologists, looking back from millions of years hence, would see our footprint clearly. A sudden spike in carbon dioxide, the spread of radioactive isotopes from nuclear weapons testing, a mass extinction event unprecedented in its speed, plastics embedded in sediments worldwide, the complete reorganization of the planet's surface, cities, roads, mines, farms, dams, the movement of species around the globe, creating a cosmopolitan fossil record where organisms from different continents suddenly appear together.
But here's the crucial question. Would they see this evidence clearly if they were looking back from 100 million years in the future? Some signatures would survive, others would fade. The isotopic anomalies, the chemical signatures, certain extinction patterns, these might persist. But the specific artifacts, the things that scream intelligence was here, those would likely be gone. This realization forces us to confront an uncomfortable possibility. Maybe we wouldn't recognize an ancient industrial civilization, even if we were staring right at its remains. There's a geological event that some researchers point to as a possible, though highly unlikely, example of what we're discussing, the Paleocene-Eocene thermal maximum, or PETM. Roughly 56 million years ago, Earth's climate went haywire. Over a period of perhaps 20,000 years, though possibly much faster, global temperatures skyrocketed by 5 to 8 degrees Celsius. The oceans acidified. Many species went extinct. Carbon dioxide flooded the atmosphere. The poles became warm enough for crocodiles and palm trees. Sound familiar?
The PETM wasn't caused by an ancient civilization. The scientific consensus attributes it to massive volcanic activity releasing carbon from organic-rich sediments, or perhaps the sudden release of methane from ocean floor deposits. But here's what makes it interesting. The PETM shows us what a rapid carbon release looks like in the geological record. It shows us the signatures we might search for. The PETM carbon isotope excursion resembles what we'd expect from burning fossil fuels. The warming pattern, the ocean acidification, the ecosystem disruption. All these echo what we're doing to the planet today. If an ancient civilization had industrialized and collapsed, might the evidence look like the PETM? Probably not. The PETM lasted too long and affected too much of the planet to be explained by a civilization's rise and fall. But it serves as a cautionary tale and a template. It shows us that Earth's climate has experienced rapid, dramatic changes before. It teaches us what to look for. And it reminds us how difficult it can be to determine the exact cause of ancient environmental catastrophes from limited geological data. Let's dream bigger. Let's push farther back into the mists of deep time. Earth is 4.5 billion years old. Life appeared, by current estimates, at least 3.5 billion years ago. But complex multicellular life, the kind that could potentially evolve intelligence, didn't emerge until much later. The first animals appeared around 600 million years ago. For billions of years, Earth was a microbial world. Or was it? Could complex life have evolved earlier, left no fossils we've recognized, and vanished? Could there have been a Precambrian civilization so ancient that all evidence has been completely erased by plate tectonics and metamorphism? This ventures into the realm of extreme speculation, but it's worth considering. The rock record from Earth's early history is fragmentary at best. Precambrian rocks have been subjected to billions of years of geological processing, heating, compression, metamorphism, erosion. Finding fossils from that era is extraordinarily difficult. Finding subtle chemical signatures of a civilization would be nearly impossible. Still, the question nags. In 4 billion years of life on Earth, in countless evolutionary experiments and extinctions and radiations, could intelligence have emerged more than once? We like to think of ourselves as unique, the pinnacle, the inevitable endpoint of evolution. But evolution doesn't work that way. Intelligence is just one strategy among many for survival. It's not inevitable, not predestined. On Earth, big brains and tool use evolved relatively recently and in only a handful of lineages. Most of life's diversity consists of organisms that get along perfectly well without human-level cognition. But given enough time, given enough dice rolls, might intelligence emerge more than once? Might there be in Earth's long history other chapters we simply can't read? The Silurian hypothesis connects to a question that has obsessed humanity since we first understood our place in the cosmos. Are we alone? The Drake equation, formulated by astronomer Frank Drake in 1961,
attempts to estimate the number of active, communicative, extraterrestrial civilizations in our galaxy. It multiplies together factors like the rate of star formation, the fraction of stars with planets, the fraction of planets that could support life, the fraction where life actually appears, the fraction where intelligent life evolves, the fraction that develops technology, and the length of time such civilizations survive. The last factor is the killer. How long does a technological civilization last? We don't know. We have only one data point, ourselves. And we're still here, still teetering on the edge of self-destruction through nuclear weapons, climate change, environmental collapse, or any number of other catastrophic possibilities.
The Silurian hypothesis adds a twist to this cosmic equation. It suggests we should ask the Drake equation not just about other worlds, but about our own. If intelligence could evolve more than once on Earth across geological timescales, then the emergence of technological civilizations might be more common than we think. But if such civilizations inevitably exhaust their planet's resources or trigger environmental collapse, they might also be short-lived and difficult to detect. This has profound implications for the search for extraterrestrial intelligence. If civilizations rarely last more than a few hundred or thousand years once they industrialize, then the galaxy might be filled with the ghosts of dead civilizations, their ruins ground to dust, their signals long since faded into cosmic background noise. We might live in a graveyard of failed experiments, searching desperately for someone, anyone, to answer our calls into the darkness. Or perhaps we're the anomaly. Perhaps we're the first in this corner of the galaxy to reach this stage. Perhaps we're the universe waking up to contemplate itself. The Silurian hypothesis doesn't answer these questions. It complicates them. And that's exactly what good science should do. So if we're serious about investigating whether a pre-human industrial civilization existed, how would we actually go about it? The search would require extraordinary detective work, combining geology, geochemistry, paleontology, climate science, and statistical analysis. We'd need to systematically examine sedimentary rocks from many time periods, looking for anomalies. This means drilling cores from ocean floors, lake beds, and other sites where sediments accumulate continuously over long periods. We'd analyze these cores for chemical signatures, unusual isotope ratios, unexpected element concentrations, anomalous organic molecules.
We'd scrutinize periods of rapid climate change, looking for fingerprints that distinguish natural variations from potential artificial forcing. This is tremendously difficult because Earth's climate system is complex and natural variability is enormous. But with sophisticated modeling and careful data analysis, we might be able to identify anomalies. Certain chemical compounds don't occur naturally or occur only in trace amounts. Industrial processes create molecules that biology doesn't produce. If we found persistent organic pollutants, synthetic polymers, or other artificial compounds in ancient rocks, that would be a smoking gun. Of course, over millions of years, even these compounds would break down, but traces might remain in the right conditions. Different processes leave different isotopic signatures. Nuclear fission produces specific isotopes that don't occur naturally in significant quantities. Industrial nitrogen fixation alters nitrogen isotope ratios. Fossil fuel combustion creates distinctive carbon isotope patterns. By carefully mapping isotope ratios across geological time, we might spot anomalies that demand explanation. The challenge is that natural processes can mimic many signatures we might associate with industrial activity. Volcanoes release carbon dioxide. Asteroid impacts create unusual chemical signatures. Natural climate variations can be rapid and severe. Ocean chemistry fluctuates. Extinction is part of the background noise of evolution. Proving the existence of an ancient civilization would require finding multiple, independent lines of evidence that converge on the same conclusion.
We'd need anomalies that cluster in time, that make sense as a package, that can't be explained by any known natural process. So far, we haven't found such evidence. But have we really been looking?
The Fermi paradox has spawned countless proposed solutions. Maybe intelligent life is rare. Maybe interstellar travel is impossible. Maybe advanced civilizations hide or transcend physical reality. Maybe they're here, and we just don't recognize them. The Silurian hypothesis suggests another possibility. Maybe civilizations don't last. Maybe there's a great filter, a challenge that technological species rarely overcome. Perhaps civilizations inevitably develop technologies that enable their own destruction faster than they develop the wisdom to use those technologies responsibly. Nuclear weapons, environmental collapse, artificial intelligence run amok, engineered pandemics. The list of potential extinction pathways grows yearly. If this is true, if technological civilizations typically last only a few hundred to a few thousand years, then the galaxy might be full of failed experiments, dead worlds, silent planets, places where intelligence arose, blazed briefly, and snuffed itself out, leaving behind only faint chemical echoes that fade over geological time. This is the dark interpretation, the pessimistic read. It suggests we're walking a knife's edge, that our survival is anything but guaranteed, that we might just be another data point in a cosmic pattern of self-destruction. But there's another interpretation, a hopeful one. If we're asking these questions, if we're aware of the risks, if we're actively working to understand our impact on the planet and change course, then maybe we're different. Maybe we're the ones who figure it out. Maybe humanity's gift isn't just intelligence, but wisdom. The ability to learn from mistakes, to adapt, to choose a different path. The Silurian hypothesis is ultimately a mirror. It reflects our fears and hopes back at us. It asks not just whether previous civilizations rose and fell, but whether we will be wise enough to avoid their fate. Let's get philosophical for a moment. The Silurian hypothesis reveals something profound about the limits of knowledge. There are events in the past that may have occurred, may have been significant, may have shaped the world we inhabit, but which are fundamentally undetectable from our current vantage point. Not undetectable because we lack the technology or haven't looked hard enough, but undetectable in principle because time has erased the evidence beyond recovery.
This is unsettling. We like to think that science, given enough effort and cleverness, can uncover all truths. But some truths may be forever beyond reach, not because they're mystical or supernatural, but simply because the universe doesn't preserve perfect records. History, even geological history, is not a complete chronicle. It's a fragmentary, biased, incomplete sampling of events. The fossil record preserves perhaps one species in 10,000. Sedimentary rocks capture only a fraction of Earth's surface environments. Plate tectonics destroys most of the ocean floor every few 100 million years. Metamorphism erases the chemical signatures of ancient rocks. We are trying to reconstruct a multi-billion-year story from scattered pages, many burned or water-damaged, with entire chapters missing. The Silurian hypothesis forces us to confront this incompleteness. It says, there are possible histories of Earth that are consistent with all available evidence, yet which we cannot prove or disprove. There are questions we can ask but never definitively answer. This doesn't mean we should give up. It means we should be humble. It means we should acknowledge uncertainty. It means we should continue investigating while recognizing the limitations of what we can know. In philosophy, this is called epistemic humility. In science, it's called being honest about your error bars. Before we go further,
we need to address something. The Silurian hypothesis is not ancient astronaut theory. It's not pseudo-archaeology. It's not an excuse to claim that aliens built the pyramids or that lizard people run the government. Unfortunately, ideas like the Silurian hypothesis can be misappropriated by those peddling nonsense. We've all seen the television shows, the books, the websites claiming that ancient civilizations possessed advanced technology given to them by extraterrestrials. These claims typically rely on ignorance of history, misunderstanding of archaeology, and a profound disrespect for the genuine achievements of ancient peoples.
The Great Pyramid of Giza is not mysterious in its construction. Ancient Egyptians were brilliant engineers working with available technology. Stonehenge, Machu Picchu, the Nazca Lines, all these monuments reflect human ingenuity, not alien intervention. The Silurian hypothesis is different. It's a thought experiment grounded in legitimate science, asking whether we could detect an industrial civilization from millions of years ago. It's not claiming such a civilization existed. It's not trying to explain human achievements by invoking ancient aliens. It's exploring the limits of geological detectability and what that means for our understanding of planetary history. This distinction matters. Science thrives on asking wild questions, exploring edge cases, pushing boundaries. But good science requires evidence, rigorous methodology, and honesty about uncertainty. Pseudoscience cherry-picks data, ignores contrary evidence, and leaps to conclusions unsupported by facts. The Silurian hypothesis invites investigation. Pseudo-archaeology demands belief. Let's address the elephant in the room, or rather, the Tyrannosaurus rex. Dinosaurs ruled Earth for 165 million years. That's an enormous span of time, dwarfing the entire existence of our species. Surely, if intelligence can evolve, it had plenty of opportunity during the Mesozoic era, right? It's a tantalizing thought. Could there have been intelligent dinosaurs? Did a species of advanced theropods develop tool use, language, culture, technology? The fossil record says no. At least it shows no evidence of it. Dinosaurs were successful, diverse, and some were certainly clever. Birds, which are living dinosaurs, display remarkable intelligence. Crows use tools. Parrots solve puzzles. Ravens plan for the future. If you've ever watched a parrot figure out how to open a latch or a crow craft a hook to retrieve food, you've witnessed dinosaurian intelligence in action. But intelligence like ours, the kind that builds civilizations, seems to require specific conditions. It needs social complexity, manual dexterity, the ability to manipulate the environment, selective pressure for problem solving, and probably a dose of luck. None of the known dinosaurs appear to have hit this particular evolutionary jackpot.
Moreover, if intelligent dinosaurs had existed and built an industrial civilization, we'd expect to find some evidence. Not necessarily cities or tools, those would erode, but we'd expect to see their fossils showing derived traits associated with intelligence, enlarged brain cases relative to body size, specialized hands capable of fine manipulation, perhaps evidence of cultural behaviors preserved in the fossil record. We see none of this. The dinosaurs were magnificent, but as far as we can tell, none were building civilizations. However, and here's where it gets interesting, the absence of evidence isn't absolute proof of absence. Fossilization is rare. Maybe an intelligent dinosaur species existed but was geographically limited, short-lived, or simply unlucky in the lottery of preservation. Maybe they existed during a period where sediments didn't accumulate in their range. Maybe their population was always small, never achieving global distribution. It's unlikely, very unlikely, but not impossible.
And that's the thing about deep time. It makes the unlikely merely improbable rather than impossible. If not dinosaurs, what about early mammals? Mammals have been around for over 200 million years. For most of that time, they were small, nocturnal creatures scurrying in the shadows of dinosaurs. But after the extinction event that wiped out the non-avian dinosaurs 66 million years ago, mammals radiated into every available ecological niche. Primates appeared roughly 65 million years ago. Apes emerged around 20 million years ago. The hominin lineage, leading to humans, split from other apes about 6-7 million years ago. Could intelligence have evolved in another mammalian lineage? Could there have been, say, 50 million years ago, a different group of smart, tool-using mammals that rose to dominance, industrialized, and vanished, leaving behind only ambiguous traces in the rock record? Again, the fossil record provides no support for this idea. We have an increasingly detailed understanding of mammalian evolution over the past 66 million years, and nothing in that record suggests a previous technological species.
But let's play devil's advocate. Suppose such a species existed, but we haven't found their fossils because they're rare, or because we haven't looked in the right places, or because we wouldn't recognize them if we saw them. What else would we expect? We'd expect evidence of their impact on the environment, large-scale changes to landscapes, domestication of other species, spread of commensal organisms following their civilization, major alterations to ecosystems. Some of these might leave traces: shifts in pollen records, changes in erosion rates, unusual distributions of species. We don't see these signatures either, at least not in patterns that suggest anything other than natural processes. The evidence, such as it is, suggests that intelligence like ours evolved only once on Earth, recently, in one particular lineage of African apes. We are, as far as we can tell, the first technological civilization this planet has produced. But can we be certain? Absolutely certain? No. We can only say that no evidence supports the existence of previous civilizations, and considerable evidence suggests we're the first. That's the honest scientific position, and it's as close to certainty as we're likely to get when investigating events from millions of years ago. Here's an unsettling thought. What if a previous civilization never lived on land? The ocean covers 71% of Earth's surface and contains 99% of the biosphere's habitable volume. It's vast, deep, and largely unexplored. We've mapped the surface of Mars in more detail than we've mapped our own ocean floor. Could an intelligent aquatic species have evolved, developed underwater technology, built civilizations in the depths, and vanished, leaving no trace we'd recognize? The ocean floor is young. Plate tectonics recycle it every 200 million years or so, dragging it into subduction zones where it melts and reforms. Any evidence older than that has literally been consumed by the planet. So if an aquatic civilization existed before about 200 million years ago, virtually all evidence would be gone, destroyed by the very geology of the planet. Even more recent evidence would be hard to find. The deep ocean is a preservational nightmare for artifacts. Anything made of metal corrodes rapidly. Anything organic gets eaten or decays. The pressure, the chemistry, the biology, all conspire to erase evidence.
Moreover, would an aquatic civilization even be recognizable as such? Would they build structures, use fire, can't have fire underwater, develop metallurgy, extremely difficult without fire, create art, writing, technology? Or would their civilization be so alien, so different from our terrestrial experience, that we simply wouldn't know what to look for? This is one of the most intriguing aspects of the Silurian hypothesis. It reminds us that our understanding of what constitutes civilization is limited by our own experience. We assume civilizations build cities, smelt metal, burn fuel, create lasting monuments. But what if intelligence can take radically different forms?
What if there are ways to be technologically sophisticated that leave no archaeological signature we'd recognize? The ocean keeps its secrets, and perhaps some of those secrets are secrets we don't even know to look for. If Earth is constantly recycling evidence, what about the Moon? The Moon has no atmosphere, no weather, no plate tectonics, no life. Once something happens on the Moon, it stays happened. The footprints Neil Armstrong left in 1969 will persist for millions of years. Every impact, every event, gets recorded in the lunar regolith and stays there. So if an ancient civilization existed on Earth and achieved spaceflight, they might have left evidence on the Moon that would persist far longer than anything on Earth. This is not as crazy as it sounds. If humans disappeared tomorrow, but some of our lunar mission's artifacts remained, those objects would outlast any trace of our civilization on Earth. In 100 million years, nothing of New York or Beijing would remain on our planet, but the lunar roving vehicle sitting on the Moon's surface would still be there, slightly degraded by micrometeorite impacts and radiation, but recognizable. So, could there be ancient artifacts on the Moon, waiting to be discovered? Could there be crash sites, abandoned bases, discarded equipment from a civilization that achieved spaceflight millions of years ago?
We haven't searched thoroughly. We've sent a few missions to limited areas of the Moon. The vast majority of its surface remains unexplored except from orbit. If ancient lunar artifacts exist, and if they're not in the few places we visited, we wouldn't know. This is genuinely exciting. It means the Moon might serve as an archive, a museum of Earth's history that preserves evidence long since destroyed on our own planet. Future lunar exploration might uncover surprises, or it might find nothing. The Moon is a big place, and artifacts would be tiny needles in an enormous haystack. Moreover, if no previous civilization existed, there will be nothing to find. But the possibility alone is worth investigating, because if we did find ancient artifacts on the Moon, it would be the most significant discovery in human history. It would rewrite everything we understand about life, intelligence, and our place in the cosmos. Let's think about technology. What does industrial civilization actually produce that might survive millions of years? We tend to think of our technology as impressive, durable, permanent. But from a geological perspective, it's incredibly ephemeral. Consider concrete. It seems solid, eternal. But concrete has a lifespan measured in decades to centuries. Rebar corrodes, concrete cracks, structures collapse. Within a few thousand years, even the most massive concrete structures would be reduced to rubble. Within 1,000,000 years, they'd be part of the sediment. Steel corrodes even faster. Aluminum, same story. Plastics, they degrade and break down. Glass returns to sand. Electronics, the most complex products of our civilization are also the most fragile, composed of materials that separate, corrode, or simply stop making sense once separated from the infrastructure that gave them purpose. Even our most ambitious projects won't last. The Hoover Dam, the Channel Tunnel, the Burj Khalifa, all will eventually crumble and disappear. In geological terms, these monuments are sand castles at high tide.
So what would last? What technological signatures might persist? Ironically, our trash might outlast our monuments. Landfills, waste sites, mine tailings, slag heaps, these might leave unusual sedimentary layers. Not because the individual objects survive, but because the chemical signature of our waste is distinctive. Future geologists might find layers enriched in heavy metals, with anomalous distributions of rare earth elements, with traces of synthetic compounds, and puzzle over what natural process could create such patterns. Nuclear waste presents a special case. The isotopes we've created through nuclear fission are distinctive and long-lived. In 1 billion years, traces of plutonium-239, neptunium-237, and other artificial radioisotopes might still be detectable in the sedimentary record. This would be a clear signature of technological activity, something that nature simply doesn't produce. But here's the catch. We've only been producing these isotopes since 1945. We're talking about less than a century of nuclear activity. Would that leave a signal detectable after 100 million years? Maybe. Maybe not. It depends on the scale of nuclear technology use, how widely it's dispersed, and whether any of it gets incorporated into sediments that happen to survive. The technological signature problem underscores how difficult it would be to detect an ancient civilization. Technology, for all its apparent permanence, is ghostly when viewed across geological time. It fades, it vanishes, it leaves behind only whispers and ambiguities. Perhaps the clearest signature of an industrial civilization would be its impact on climate. We are conducting a planetary-scale experiment right now, pumping billions of tons of carbon dioxide into the atmosphere, warming the planet, acidifying the oceans, disrupting weather patterns. This is creating geological evidence that should persist for millions of years. The isotopic signature of fossil fuel burning, the extinction event we're causing, the redistribution of species, the chemical changes in the ocean. Would a previous civilization have done the same thing?
It's hard to imagine how you get to industrial civilization without an energy crisis and without exploiting stored chemical energy, which means fossil fuels or something similar. Any civilization going through an industrial revolution would likely burn through ancient carbon stores, releasing that carbon into the atmosphere, warming the planet. This should create a detectable signal, a spike in atmospheric CO2 preserved as changes in carbonate chemistry in ocean sediments, accompanied by warming signatures in temperature proxies, possibly followed by a recovery as the carbon gets reabsorbed into rock and ocean over hundreds of thousands of years. The question is whether we could distinguish this from natural climate variations. Earth has experienced many episodes of rapid warming and high CO2 levels. The PETM we discussed earlier is one example. Others include the Toarcian oceanic anoxic event around 183 million years ago, the Cernamian-Turonian boundary event 94 million years ago, and several others. Each of these events has a natural explanation: massive volcanism, methane release, changes in ocean circulation. But could any of them be hiding the signature of an ancient civilization? Probably not. The scale and duration of these events don't quite match what we'd expect from a civilization's rise and fall. They affect too much of the planet, last too long, and have clear connections to volcanic or tectonic activity. But they teach us what to look for. They show us the kinds of signals an ancient industrial civilization might leave. And they remind us that climate change is written in stone, literally, in the chemistry of rocks formed during periods of environmental upheaval. Let's zoom out for a moment and consider our planet in cosmic context. Earth is special. Not unique necessarily, but certainly unusual. We orbit a stable, long-lived star at just the right distance for liquid water to exist. We have a large moon that stabilizes our axial tilt, preventing wild climate swings. We have plate tectonics that recycles carbon and regulates climate over geological time. We have a magnetic field that protects us from solar radiation. We have the right mix of elements for complex chemistry. It's hard to imagine how you get to industrial civilization without an energy crisis and without exploiting stored chemical energy, which means fossil fuels or something similar. Any civilization going through an industrial revolution would likely burn through ancient carbon stores, releasing that carbon into the atmosphere, warming the planet. This should create a detectable signal, a spike in atmospheric CO2 preserved as changes in carbonate chemistry in ocean sediments, accompanied by warming signatures in temperature proxies, possibly followed by a recovery as the carbon gets reabsorbed into rock and ocean over hundreds of thousands of years. The question is whether we could distinguish this from natural climate variations. Earth has experienced many episodes of rapid warming and high CO2 levels. The PETM we discussed earlier is one example.
Others include the Toarcian oceanic anoxic event around 183 million years ago, the Cernamian-Turonian boundary event 94 million years ago, and several others. Each of these events has a natural explanation: massive volcanism, methane release, changes in ocean circulation. But could any of them be hiding the signature of an ancient civilization? Probably not. The scale and duration of these events don't quite match what we'd expect from a civilization's rise and fall. They affect too much of the planet, last too long, and have clear connections to volcanic or tectonic activity. But they teach us what to look for. They show us the kinds of signals an ancient industrial civilization might leave. And they remind us that climate change is written in stone, literally, in the chemistry of rocks formed during periods of environmental upheaval. Let's zoom out for a moment and consider our planet in cosmic context. Earth is special. Not unique necessarily, but certainly unusual. We orbit a stable, long-lived star at just the right distance for liquid water to exist. We have a large moon that stabilizes our axial tilt, preventing wild climate swings. We have plate tectonics that recycles carbon and regulates climate over geological time. We have a magnetic field that protects us from solar radiation. We have the right mix of elements for complex chemistry.
The rare Earth hypothesis, proposed by Peter Ward and Donald Brownlee, argues that while simple life might be common in the universe, complex life requiring very specific conditions is rare. Earth-like planets with Earth-like histories might be vanishingly uncommon. If this is true, then intelligent life is probably rare as well. And if intelligence rarely evolves, then multiple instances of intelligence on a single planet becomes even less likely. This doesn't disprove the Silurian hypothesis, but it provides context. It suggests that while we can't rule out a previous civilization on Earth, we shouldn't expect one. The conditions that allowed intelligence to evolve in the hominin lineage might be unique, or at least unusual in Earth's history. But here's a counterargument. If Earth is particularly good at producing conditions for complex life, might it also be particularly good at producing intelligence? If the planet has been habitable for billions of years, if complex life has existed for hundreds of millions of years, if the stage has been set for intelligence again and again, might evolution have found that solution more than once? Intelligence isn't a single trait, it's a complex suite of adaptations. Advanced cognition, social behavior, communication, tool use, forward planning. These traits have evolved independently in multiple lineages: primates, corvids, parrots, cetaceans, elephants, octopuses. None of these, except humans, achieved technological civilization, but they demonstrate that the building blocks of intelligence can emerge independently. So, while Earth might be rare in the cosmos, intelligence might not be as rare on Earth as we assume. Given enough evolutionary time, enough extinction events shuffling the deck, enough opportunities for new lineages to explore cognitive niches, might intelligence emerge more than once? It's possible. Not proven, not even particularly likely, but possible. And possibility is all the Silurian hypothesis asks for.
Let's engage in some speculative anthropology, or rather, speculative sophontology, the study of intelligent beings. Suppose an intelligent species did evolve millions of years ago. Would they necessarily develop industrial civilization? Humans industrialized because of a specific constellation of factors. We had hands capable of precise manipulation. We discovered agriculture, which allowed population growth and specialization. We developed writing, which enabled knowledge accumulation. We happened to have accessible deposits of coal and later oil. We had social structures that supported innovation, and we had cultural drives toward expansion and resource exploitation. Change any of these factors, and history might have unfolded differently. A species with dolphin-like intelligence but no hands couldn't build machines. A species living in a paradise of abundant resources might never develop agriculture or feel pressure to innovate. A species with different social structures might not accumulate knowledge across generations. Moreover, industrial civilization might not be an inevitable endpoint of intelligence. It's one path among many. Perhaps other intelligent species would make different choices, develop different technologies, create societies that leave different signatures on the planet. We assume that advanced means industrial, but that's a very human assumption. An intelligent species might develop sophisticated social technologies, rich cultures, complex languages, and never build a single factory. They might thrive for millions of years without ever entering an industrial age, living in balance with their environment, leaving traces indistinguishable from any other successful species. This raises a profound question. Are we looking for the wrong thing? Are we searching for evidence of industrial civilization because that's what we know, while other forms of advanced intelligence might leave signatures we don't recognize?
The Silurian hypothesis asks if we could detect a previous civilization. But maybe the deeper question is, what counts as civilization? What counts as advanced? What counts as success? If a species survives and thrives for 10 million years without destroying its environment, is that not more successful than a species that industrializes, reaches for the stars, and collapses within 10,000 years? These are not questions science can answer definitively. They touch on values, definitions, perspectives. But they're worth asking as we contemplate our place in the grand history of this planet. Earth's history is punctuated by mass extinctions, 5 major ones, plus numerous smaller events. Each extinction represents catastrophe, the end of dominant lineages, the collapse of ecosystems. But each is also followed by renewal, by adaptive radiation, by the emergence of new forms exploiting the vacant ecological niches left by the dead. The extinction that killed the non-avian dinosaurs 66 million years ago opened the way for mammals to diversify, and eventually for primates and ultimately humans to evolve. Without that asteroid impact, we wouldn't be here. So here's a thought. Maybe previous intelligent species did exist, and maybe they contributed to their own extinction through environmental catastrophe. And maybe their disappearance was necessary for our emergence. Maybe Earth has hosted multiple experiments in intelligence, each ending in failure, each clearing the stage for the next attempt. Maybe we're the latest iteration, not the first, learning the lessons that previous civilizations learned too late. This is deeply speculative, bordering on mythology, but it's a framework for thinking about deep time and the role of intelligence in planetary history. It suggests that intelligence might be recurring but fragile, repeatedly emerging and repeatedly self-destructing, with each iteration leaving faint traces that the next iteration struggles to interpret. If this were true, what would it mean for us? It would mean we're walking a path others have walked before. It would mean the challenges we face, climate change, resource depletion, weapons of mass destruction, aren't unique to us, but are perhaps inevitable challenges for any technological species. It would mean the Great Filter might be behind us or ahead of us, but either way, it's real.
And it would mean that survival isn't guaranteed. Success isn't inevitable. We could fail, as others might have failed before us. We could become another ambiguous layer in the geological record, another isotopic anomaly that future investigators puzzle over. Or we could learn. We could be the ones who figure it out, who thread the needle, who build a civilization that lasts not centuries or millennia, but millions of years, who become not a cautionary tale, but a triumph. The choice, as far as we can tell, is ours. Nikolai Kardashev, a Russian astrophysicist, proposed a scale for classifying civilizations based on energy use. A Type 1 civilization harnesses all the energy available on its planet. A Type 2 harnesses all the energy of its star. A Type 3 harnesses all the energy of its galaxy. Humanity is currently about 0.7 on this scale. We use a fraction of the total energy reaching Earth from the Sun. We're approaching Type 1 status, but haven't achieved it yet. The Silurian hypothesis intersects interestingly with the Kardashev scale. If a previous civilization existed and collapsed, what level had they reached? Probably not beyond Type 1. A civilization that had achieved Type 2 status, building megastructures around the Sun, would have left evidence we definitely detect. Massive engineering projects in the inner solar system would leave permanent traces. So any hypothetical previous civilization was likely confined to Earth, using a fraction of planetary resources, just like us. This suggests that if such civilizations existed, they faced the same challenges we face. They were bound by the same physical limits. They dealt with the same constraints on growth, the same energy bottlenecks, the same environmental feedback. And if they failed to move beyond planetary civilization, if they collapsed before achieving interstellar capability, then they were vulnerable to the same catastrophes that threaten us: resource depletion, environmental collapse, self-destruction through war or pollution. This is the sobering message of the Silurian hypothesis. It doesn't just ask whether previous civilizations existed. It asks whether any planetary civilization can survive long enough to become something more. Because if the answer is no, if there's a ceiling that technological species repeatedly hit and fail to break through, then the universe might be full of silent planets where intelligence sparked briefly and died, never escaping the cradle that birthed it. That would be a lonely cosmos indeed.
Human civilization has existed in its current form for perhaps 10,000 years since agriculture. For most of that time, we had no concept of deep time, no understanding of the planet's age, no appreciation for the vast sweep of geological history. The idea that Earth is billions of years old is new. Biblical scholars once calculated Earth's age at around 6,000 years. This wasn't stupidity. It was working with available evidence and cultural frameworks. The concept of deep time, of millions and billions of years, emerged only in the 19th century as geologists studied rock layers and realized the story they told required unimaginable spans of time. We are newcomers to understanding our planet's history. We've only been seriously studying geology for about 200 years. We've only understood plate tectonics since the 1960s. We've only had radiometric dating, allowing precise age determination of rocks, since the early 20th century. Given how recent our understanding is, how much might we still not know? How many chapters of Earth's history remain unread? The Silurian hypothesis reminds us that absence of evidence is not evidence of absence, especially when the evidence would be subtle, ancient, and difficult to detect. It reminds us that there are things we don't know that we don't know. This isn't an argument for believing in ancient civilizations without evidence. It's an argument for intellectual humility. It's a reminder that science is an ongoing process, that our understanding evolves, that certainty is elusive when investigating events from millions of years ago. We should be confident in what the evidence shows, but humble about what it might not show. We should keep searching, keep questioning, keep testing hypotheses, even ones that seem unlikely, because the universe has surprised us before, and it will surprise us again.
The search for extraterrestrial intelligence has been ongoing for decades. We've listened for radio signals, looked for optical pulses, searched for signs of megastructures or planetary engineering. We found nothing. The Fermi paradox looms large. Where is everybody? The Silurian hypothesis offers a potential answer. Maybe they existed, flourished briefly, and collapsed. leaving behind only faint traces or nothing at all. Maybe the galaxy is filled with the ghosts of dead civilizations, species that reached for the stars but failed to grasp them, that industrialized but couldn't sustain it, that developed technology but not wisdom. If this is true, then SETI might be searching for something that rarely exists at any given moment: active technological civilizations. The window during which such civilizations broadcast detectable signals might be tiny, just a few hundred or thousand years. The odds of two civilizations existing simultaneously, close enough for communication, become vanishingly small. This is the pessimistic view. But there's an optimistic interpretation as well. If intelligence has evolved on Earth at least once, and possibly more than once, then the emergence of intelligence might be more common than we think. The galaxy might be full of planets where intelligence evolves, disappears, and evolves again, a recurring pattern over billions of years. In that case, intelligence isn't rare, it's just fragile and episodic. This would suggest that the challenge isn't making intelligence emerge, it's making it last. The great filter isn't behind us, it's ahead, and it's the challenge of building sustainable civilization.
Throughout this essay, we've been thinking about intelligence in human terms. We imagine previous civilizations that looked like ours, building cities, using tools, altering environments, developing technology. But intelligence might take forms we can't imagine. It might arise in substrates we don't recognize. It might leave signatures we're not looking for. Consider the octopus. It's intelligent by many measures. It solves puzzles, uses tools, shows individual personality, demonstrates learning and memory. Its brain is organized completely differently from ours, with most of its neurons distributed in its arms rather than centralized. It's an example of convergent evolution of intelligence along a radically different path. Now imagine an octopus-like intelligence that evolves over millions of years. It never develops human-style technology because it lives underwater and has no access to fire or metallurgy. But it develops sophisticated social structures, communication systems, perhaps even a form of culture. Is this civilization? By some definitions, yes. By others, no. The point is that our search for previous civilizations is inevitably biased by what we think civilizations should look like. We're looking for versions of ourselves translated into the past. We might completely miss forms of intelligence and culture that don't fit our preconceptions. This is the anthropocentric trap. We assume that intelligence naturally leads to technology, that technology naturally leads to industrialization, that industrialization naturally leaves detectable signatures. But these assumptions are based on a sample size of one, us. Maybe there are other paths. Maybe intelligence can be successful without technology. Maybe technology can exist without leaving geological signatures. Maybe civilization can thrive for millions of years while remaining invisible to future archaeologists. If so, then the Silurian hypothesis becomes even more interesting and even more difficult to test. Because we're not just asking if previous civilizations existed, we're asking if we would recognize them if they had.
Let's pull back one more time and look at Earth from the cosmos. Our planet is a pale blue dot, as Carl Sagan famously called it, a mote of dust suspended in a sunbeam. One world among billions in our galaxy, in a galaxy among billions in the observable universe. From this perspective, the Silurian hypothesis takes on cosmic significance. If intelligence can evolve more than once on a single planet, given enough time, then the universe might be far richer in intelligence than we thought. Every Earth-like world, given billions of years, might host multiple experiments in consciousness, multiple attempts at civilization, multiple stories of rise and fall. The cosmos might be populated not by civilizations in the sense of ongoing empires spanning stars, but by brief sparks of intelligence, flashing into existence, burning brightly for a geological instant, and fading away, leaving behind only the faintest traces.
From this view, we are not unique. We are participants in a cosmic pattern, part of a grand experiment the universe is conducting in complexity and consciousness. We are one iteration among countless others on this world and potentially on others. This should be humbling. It should make us less arrogant about our place in the cosmos, but it should also be inspiring. Because if intelligence repeatedly emerges, if consciousness is a natural phenomenon given the right conditions, then we are part of something larger than ourselves. We are the universe waking up, looking around and asking questions. And maybe, just maybe, we're the iteration that figures it out. Maybe we're the ones who learn from the mistakes of those who came before, whether we can prove they existed or not. Maybe we're the ones who build a civilization that doesn't just flash and fade, but endures. That's worth striving for. So where does this leave us? We've explored a thought experiment, considered its implications, examined the evidence, or lack thereof. What are we supposed to do with this information? First, take it seriously as a scientific question. The Silurian hypothesis identifies a genuine gap in our knowledge and a real limitation in our ability to reconstruct deep time. It's worth investigating, worth developing methodologies to search for ancient industrial signatures, worth keeping open minds about what we might find.
This doesn't mean believing in ancient civilizations without evidence. It means acknowledging that certain questions are difficult to answer definitively, and that we should continue searching. Second, use it as a lens for understanding our own civilization. The Silurian hypothesis asks what traces we're leaving, how long they'll last, whether future investigators could reconstruct our existence from fragmentary evidence. This forces us to think about our impact on the planet, about sustainability, about the long-term consequences of our actions. We are creating geological signatures right now. Future beings, whether human or otherwise, will judge us by what we leave behind. Will they find evidence of a wise civilization that learned to live in balance with its environment? Or will they find the chemical signatures of a species that burned through its planet's resources in a geological eye blink? Third, let it inform our search for extraterrestrial life. If civilizations are brief and difficult to detect even on their home planets, what does that mean for finding them across interstellar distances? It suggests we should broaden our search criteria, look for subtle signatures, expect ambiguity rather than clarity. Fourth, embrace the humility it demands. We don't know everything. We can't know everything. Some questions might be forever unanswerable. That's okay. That's part of the human condition. We search for truth while acknowledging the limits of what we can find. And finally, be inspired by the sheer scale of the question. The Silurian hypothesis connects deep time with the future, geology with philosophy, science with imagination. It asks us to think bigger, to consider possibilities beyond our immediate experience, to remain curious about the world we inhabit. That curiosity, that willingness to ask wild questions and take them seriously, that's what makes us human. That's what makes us scientists. That's what makes us dreamers. In the end, the Silurian hypothesis is a mirror. When we look for evidence of previous civilizations, we're really examining ourselves. When we ask whether we'd recognize the traces of an ancient industrial society, we're asking what traces we're leaving. When we wonder if a previous civilization collapsed due to environmental catastrophe, we're confronting our own potential fate. The hypothesis forces us to think about time, about legacy, about meaning. It asks what it means to exist briefly on a planet that measures existence in eons. It asks whether our monuments will last, whether our achievements will be remembered,
whether our existence will matter in the grand sweep of planetary history. These are not comfortable questions. They challenge our ego, our assumption of centrality, our belief that we're special or unique or permanent. They remind us that we are small, brief, and fragile. But they also remind us that we are part of something magnificent. We are participants in the story of a living planet and the evolution of complexity, in the emergence of consciousness. We are the universe reflecting on itself, even if only for a moment. And moments matter, even brief ones, even ones that leave no lasting trace. The Silurian hypothesis will probably never be definitively proven or disproven. We will probably never find clear evidence of a previous industrial civilization on Earth. The geological record is too fragmentary, the time too vast, the signatures too subtle. But the Silurian hypothesis has already served its purpose. It has made us think. It has expanded our perspective. It has forced us to confront the limits of knowledge and the depths of time. It has connected disparate fields: geology, paleontology, climate science, astrobiology, philosophy. It has asked us to imagine the unimaginable and to take that imagination seriously. That's what good science does. It doesn't just answer questions, it asks better questions. It doesn't just solve problems, it reveals new problems we didn't know existed. It doesn't just add to our knowledge, it expands the space of what we understand to be knowable. The Silurian hypothesis is a reminder that the universe is stranger, more complex, and more interesting than we give it credit for. It's a reminder that absence of evidence is not always evidence of absence. It's a reminder that humility is a scientific virtue. And perhaps most importantly, it's a reminder that we are living through an extraordinary moment in planetary history. We are the first civilization on Earth that we know of, possibly the first that has ever existed. We are writing a chapter in Earth's story that future beings might puzzle over, might struggle to interpret, might find ambiguous or clear, depending on what we do next.
That brings us to the heart of the matter. If we take the Silurian hypothesis seriously, it places an enormous weight of responsibility on our shoulders. We are, as far as we know, the only technological civilization this planet has produced in 4 billion years of life. We are Earth's ambassadors to the cosmos, the planet's means of understanding itself. We are carriers of consciousness and culture, of art and science, of everything that makes existence meaningful rather than merely mechanical. If we fail, if we collapse, if we become another ambiguous layer in the geological record, then we've squandered something precious, not just human life, though that matters enormously, but the opportunity for intelligence to persist, to learn, to grow, to understand, to explore. We have responsibilities to the past, to the billions of years of evolution that led to us, to the countless organisms whose lives and deaths built the biosphere we inhabit, to the planet itself, which provided the stage for life's great drama. We have responsibilities to the present, to each other, to the 7 billion people sharing this planet, to the millions of species with whom we share this world, to the ecosystems that sustain all life. And we have responsibilities to the future, to the generations yet unborn, to the potential civilizations that might follow us if we fail, to the possibility of intelligence spreading beyond Earth to other worlds, to the cosmic significance of consciousness persisting and flourishing. These are heavy responsibilities. No one asked if we wanted them, but we have them nonetheless,
by virtue of being who and what and when we are.
What then should we do? The answer isn't mysterious or complicated. We should do what we know we should do, what we've known for decades but have been reluctant to fully embrace. We should transition to sustainable energy systems that don't poison our atmosphere or destabilize our climate. We should protect and restore the biosphere, recognizing that we are part of it, dependent on it, responsible for it. We should develop technologies that work with natural systems rather than against them. We should distribute resources more equitably so that all humans can thrive rather than merely survive. We should invest in education, in science, in the search for knowledge and wisdom. We should prepare for the long term, not just planning for the next quarter or the next election cycle, but thinking in terms of centuries and millennia. We should ask ourselves what kind of world we want to leave for the 100th generation hence, for the 1000th generation, for the civilizations that might follow us if we succeed in building something lasting. We should also reach outward. We should continue exploring space, not to escape Earth, but to expand the scope of life and intelligence. We should search for other civilizations while recognizing we might be alone, and that being alone carries its own kind of responsibility. And we should tell stories. We should preserve knowledge. We should create art and culture and meaning, because even if our physical traces fade, even if our cities crumble and our technologies corrode, the ideas we generate, the beauty we create, the understanding we achieve, these have value independent of their durability. Imagine, for a moment, that you could send a message to a future civilization, not human necessarily, perhaps something that evolves from corvids or octopuses, or a lineage we can't predict, a species that emerges millions of years hence and develops the capability to investigate Earth's past. What would you want them to know about us? That we were here? That we tried? That we created beauty and sought knowledge and loved each other and struggled with the enormous challenges of our time?
That we recognized, perhaps too late, that we were connected to everything, that our actions had consequences, that we were responsible for the world we inherited and the world we would leave behind, that we asked questions like these, that we wondered about those who came before, that we thought about those who would come after. Perhaps that's enough. Perhaps knowing that intelligence existed, that it asked questions, that it created and wondered and struggled, perhaps that alone would be meaningful to future investigators. Or perhaps they would judge us more harshly. Perhaps they would see the extinctions we caused, the climate we disrupted, the opportunities we squandered. Perhaps they would shake their heads, or whatever appendages they use for such gestures, and add us to the list of civilizations that failed. We don't know how the story ends. We're still writing it. The Silurian hypothesis asks, were there others before us? But implicit in that question is another. Will there be others after us? If we fail, if we collapse, will another intelligent species eventually evolve? Will Earth get another chance? Will the planet that produced us produce something else, perhaps wiser, perhaps more successful at building sustainable civilization? Or are we it? Are we the only shot this planet gets at technological intelligence? If we fail, does the experiment end? We can't know. Evolution is contingent, unpredictable. Intelligence emerged once. It might emerge again. Or it might not. The conditions that led to human evolution might be unique, unrepeatable. But this uncertainty should focus our minds wonderfully. If we might be Earth's only chance, if no one is coming to clean up our mess or carry the torch forward, then we'd better get it right. And even if other chances exist, even if the planet would eventually produce other intelligent species, that doesn't absolve us of responsibility. We are here now. We are conscious now. We are capable of action now. The future might be written by others, but the present is written by us.
Sometimes, late at night, When the world is quiet and you're alone with your thoughts, do you ever feel the weight of deep time? Do you ever sense the vast ages that preceded you, the billions of years when Earth existed without human eyes to see it, without human minds to comprehend it? Do you ever imagine the eons that might follow, the long future stretching ahead, the ages when we might be gone and other beings might walk where we walked, swim where we swam, fly where we flew? The Silurian hypothesis lives in that silence, in that space between what we know and what we can never know, in the gaps in the geological record, in the ambiguities of ancient rocks, in the mysteries that time keeps locked away. It whispers, "You are not necessarily the first, and you might not be the last, but you are here now, and now is what matters." If the Silurian hypothesis teaches us anything, it's that civilizations are fragile. They are brief sparks in the darkness of geological time. They can rise and fall and vanish, leaving behind traces so faint they might never be found. But it also teaches us that the universe is patient, Earth is patient, life is persistent. Given time, given opportunity, complexity emerges, consciousness arises, intelligence appears. The pattern might repeat, the experiment might run again, the universe might get another chance to understand itself. But we shouldn't count on that. We should assume this is our only chance, our only moment, our only opportunity to do something meaningful with the gift of consciousness. We should assume that we matter, that our choices matter, that the future depends on what we do right now. Because even if we're wrong, even if other chances exist, living as if we matter, and as if our choices have consequences, is the only way to build something worth building. Despite everything, despite the challenges and the dangers and the very real possibility of failure, there is reason for hope. We are asking these questions. We are thinking about our impact. We are beginning, however slowly and imperfectly, to change course. We are recognizing that business as usual leads to catastrophe, and that we need new ways of thinking, new ways of organizing society, new relationships with the planet and with each other.
The fact that scientists proposed the Silurian hypothesis at all is hopeful. It means we're thinking about long-term consequences. It means we're examining our place in planetary history. It means we're taking seriously the idea that our actions have geological significance. Young people around the world are demanding action on climate change. Scientists are developing clean technologies. Engineers are designing sustainable systems. Activists are pushing for environmental protection. Artists are imagining better futures. Philosophers are grappling with the ethical dimensions of our planetary crisis. This isn't enough yet. We're not moving fast enough, doing enough, changing enough. But the stirrings are there. The awareness is growing. The possibility of transformation exists. We could fail. The odds, frankly, aren't great. But we could also succeed. We could be the civilization that figures it out, that threads the needle, that builds something lasting. We could be the ones who, when future beings investigate Earth's history, leave behind not just chemical signatures of industrial collapse, but evidence of wisdom, of learning, of choosing a better path. So let's return to where we began. What if we are not the first civilization on Earth? We've explored this question from every angle. We've considered the evidence and the lack thereof. We've examined what traces ancient civilizations might leave and how difficult they'd be to detect. We've thought about deep time and geological recycling and the limits of knowledge. And the answer is, we don't know. We probably never will know with certainty. The question might be fundamentally unanswerable. But that's not the point. The point is that asking the question changes how we think about ourselves, about time, about our place in the planetary story. If we are the first, then we carry the responsibility of being pioneers, of setting the template, of showing what's possible. If we are not the first, if others came before and failed, then we carry the responsibility of learning from their failures, of doing better, of breaking the pattern. Either way, the responsibility is ours. Either way, the future depends on what we do now. Either way, we are writing a chapter in Earth's history that will be read, if it's read at all, with difficulty and ambiguity by those who come after.
Let's make it a chapter worth reading. Let's make it a story of triumph rather than tragedy. Let's make it evidence that intelligence can be wise, that civilization can be sustainable, that consciousness can persist and flourish and spread. Let's make it a legacy we'd be proud to leave behind. Because whether we're the first or the 100th, whether we're unique or part of a pattern, whether we're alone in the cosmos or one among many, we are here now. We are conscious now. We are capable of action now. And now is all we have. Now is everything.